Somewhere in your home right now, there is a piece of copper wire doing absolutely nothing. And that piece of wire might be the reason your internet is slower than it should be. I know that sounds like the setup to a bad infomercial, but stay with me for just a moment, because what I'm about to walk you through is rooted in antenna physics that's been understood for over a century. It's just never made its way to the average person's living room. And honestly, that's not an accident. It's just not the kind of thing that generates a service call or a hardware upgrade sale. Let me show you exactly what's going on with your router, why your Wi-Fi underperforms by default, and how a single loop of copper wire, something you might already own, can meaningfully change how your signal behaves in your home. Let's talk about what's actually happening inside that little box on your shelf, because most people have no idea how badly their router is working against them by default. Your router is broadcasting a wireless signal in every direction simultaneously. Up, down, sideways, through the floor, toward the ceiling, in a rough sphere of electromagnetic energy. Now, if you live in a multi-story house, maybe half of that broadcast is going straight up into the ceiling or down through the floor. Rooms you might not even use. If you live in an apartment, you're sending signal into your neighbor's unit. Signal that should be reaching your phone, your laptop, your streaming device. It's just leaving, going nowhere useful. Router manufacturers design their devices to broadcast in every direction because that's the safest assumption. They have no idea where you'll put the device, where your walls are, or which direction your devices are. So they design for average everywhere, which ends up being optimal nowhere. And here's the thing, the antennas built into your router are functional. They're not bad antennas, but they're designed for general, unspecific use. They are not designed for your home. They're not calibrated for the specific distances, obstacles, and device positions in your specific space. So when you're sitting 15 feet from your router and your video keeps buffering, it's not necessarily because your internet plan is too slow. It may be because you're only receiving a fraction of the signal your router is actually capable of delivering, because most of it went somewhere else. This is the real problem, not speed, distribution. And the copper wire fix addresses exactly this. Here's something that electrical engineers learn in their first year that almost never makes it into a conversation about home internet. Every antenna, whether it's a massive broadcast tower or the little stick poking out of your router, works by converting electrical current into electromagnetic waves. That's it. That's the whole trick. You run alternating current through a conductor, and the changing electrical field generates a corresponding magnetic field, and that ripple of energy propagates outward through space as a radio wave. Now, what determines how that energy propagates? What shape the broadcast pattern takes has a lot to do with the geometry of the conductor and what's around it. This is where something called passive resonance comes in. When you place a conductor near an antenna, even one that isn't electrically connected to the circuit, if that conductor's geometry resonates with the signal's frequency, it interacts with the electromagnetic field. It can redirect energy, concentrate it. In some configurations, it acts like a passive reflector or a directional guide. Amateur radio operators have understood this for decades. They call it a parasitic element. A nearby conductor that's tuned, even loosely, to the signal frequency will couple with the primary radiating element and reshape the radiation pattern. It's the same principle behind Yagi antennas, which are those old-fashioned TV antennas that look like a fishbone. Multiple rods, only one of which is actually connected to the wire going into your TV. The others are parasitic, passive. They're just shaped metal influencing the propagation of the signal. Your router operates at 2.4 GHz or 5 GHz. Both are radio frequencies, which means the physics that applies to a ham radio antenna or a television aerial also applies, in principle, to the device sitting on your bookshelf. That's the foundation of what we're going to do. Copper isn't just a cheap metal. From an electromagnetic standpoint, it's one of the most cooperative materials on the planet. It has one of the highest electrical conductivities of any commonly available material. Silver is slightly better, gold after that, but copper is what makes practical electronics possible because it's abundant, affordable, and easy to work with. Your house is wired with it. Phone chargers use it. It's everywhere. When we wrap copper wire around or near a router antenna, what we're doing is creating a passive resonance structure, a loop or coil of highly conductive material positioned in the near field of the antenna's electromagnetic radiation. Now, I want to be precise here, because precision matters. The results of this technique are going to vary depending on your specific router, antenna design, frequency band, and home environment. What the copper wire does, when positioned correctly, is interact with the router's radiated field in a way that can concentrate signal energy in particular directions, rather than allowing it to dissipate uniformly in all directions. Think of it like cupping your hands around your mouth when you want to project your voice. You're not generating more sound. You're redirecting what's already there. Same total energy, different distribution. For people whose primary devices are in one general direction from their router, this redirection can mean a meaningfully stronger, more stable signal where they actually need it. Some people who have tried this report noticeable improvements in signal strength readings on their devices. Others see moderate improvement. A small number notice minimal change, particularly in environments where other interference factors dominate. The results are real, but they are not uniform. And I'd rather tell you that up front than oversell this and lose your trust. What's consistent is the mechanism. The physics is real. The variation is in execution and environment. Alright, here is exactly what you're going to do. And I want you to pay attention to the details because the specifics here actually matter. You need solid core copper wire. Not stranded, not coated aluminum, not speaker wire. Solid core copper. The kind used in household electrical work is ideal. The gauge doesn't need to be precise. 18 to 22 gauge is a reasonable range. Hardware stores carry this. You might already have a piece in your garage or utility drawer. You also need a way to form the wire. Your hands, a cylindrical object to wrap around, a marker, a pen, a small bottle, and a pair of wire cutters or scissors if the wire is thin enough. Step 1. Identify your router's external antennas. Most home routers have 1, 2, or 3 external antennas, those adjustable rods that stick up from the body of the device. If your router has no external antennas and uses internal antennas only, the external wrap technique applies to the router body itself and will address that variation in a moment. Step 2. Cut a length of copper wire that is approximately 12 centimeters, about 4.7 inches. This length is chosen because it corresponds roughly to a half wavelength at 2.4 GHz, which is the lower of the two common Wi-Fi bands and the one that penetrates walls most effectively. If you're primarily using 5 GHz, which offers faster speeds over shorter distances, cut approximately 6 centimeters or about 2.4 inches instead. Step 3. Form the wire into a loose coil or loop. You don't need perfect geometry here, but you want a circular or near circular shape. Wrap it around a marker or similar cylindrical object 3 to 4 times to create a tight coil, then slide it off. The inside diameter of the coil should be roughly the same as the diameter of your router's antenna, just wide enough to slide over. Step 4. Slide the copper coil over one of your router's external antennas. Position it approximately in the middle of the antenna's length. It should sit there loosely. No need to tape it or attach it firmly. The contact is not electrical, it's positional. You're placing it in the near field of the antenna, not connecting it to the circuit. Step 5. Adjust your router so its antennas are pointing vertically, straight up. This is the standard recommended orientation for omnidirectional signal propagation, and the copper coil works best with this geometry. Step 6. Check your signal. Use a Wi-Fi analyzer app on your phone or laptop. There are several free options available, and note the signal strength in the rooms or areas where you most need coverage. Compare before and after at the same distance and location. If you have a router with only internal antennas, the approach is slightly different. In that case, coil the wire, a slightly larger diameter coil, and position it flat against the top surface of the router body or loop it around the outside of the router's casing. The internal antennas are still broadcasting through the plastic casing, and the copper in proximity will still interact with that field, though typically with less precise effect than an external antenna application. Now, let me be straight with you about what you'll actually notice, because I'm not going to sit here and promise you magic. In a typical home setup, the most common result people observe is an improvement in signal consistency. Fewer drops, more stable connection at the edges of coverage range. In some setups, particularly where the router and primary devices are in the same general horizontal plane, there are also measurable improvements in signal strength at distance. The factors that influence how much improvement you see include the design of your specific router's antenna, the layout of your home, the materials in your walls. Concrete absorbs signal significantly more than drywall, for example, and whether you're on 2.4 or 5 GHz. One factor worth mentioning: if your internet issue is not signal strength but actual bandwidth, meaning you're paying for a plan that simply doesn't deliver the speeds you're expecting, then this technique will not solve that problem. What it addresses is the distribution and retention of the signal your router is already producing. If the signal coming into your home is limited by your plan or your modem, the copper coil won't change that upstream constraint. Use this for what it is: a signal optimization technique, not an infrastructure replacement. You might be wondering, if this is based on real antenna science, why hasn't anyone told you about it before? The honest answer is straightforward and has very little to do with anything dramatic. Your internet service provider sells you a speed tier. They don't have a financial interest in helping you optimize your in-home signal distribution, because your in-home setup is technically your responsibility past the modem. Their job, contractually, ends at the point the signal enters your home. Router manufacturers are similarly incentivized. They make money when you upgrade to a newer model, a Wi-Fi 6 router, a mesh system, another access point. A piece of copper wire you already own doesn't generate revenue for anyone. This isn't a conspiracy. It's just how incentives work in a market. The knowledge exists. It lives in electrical engineering curricula, in amateur radio forums, in antenna theory textbooks. It's not hidden. It's just not promoted, because there's no profit in promoting it. And that honestly is true of a lot of practical knowledge. The reason you're hearing about it here is because the goal isn't to sell you hardware. The goal is to give you something useful. Once you've tried the basic wrap, there are a couple of variations that some people have found push the results even further. The first is the double band configuration. If your router has 2 external antennas, which many dual band routers do, prepare 2 coils, one cut to the 2.4 GHz half wavelength at 12 centimeters and one cut to the 5 GHz half wavelength at 6 centimeters. Apply one coil to each antenna. This way you're potentially influencing both frequency bands rather than just one. The second variation involves positioning. Instead of centering the coil on the antenna, try sliding it towards the base, closer to where the antenna connects to the router body. Some users report this produces a slightly more focused horizontal dispersion, which can be advantageous if all your devices are in one room. The third, for those with internal antenna routers, is using a flat spiral rather than a cylindrical coil. Wind the copper wire into a flat, disc-shaped spiral about 8 to 10 centimeters in diameter and place it flat on top of the router. The larger contact area with the router's radiated near field can produce a more noticeable interaction than a simple loop. Experiment with these. Your home environment is unique, and what works best is worth a few minutes of testing. Here's what I want you to take away from all of this. Your internet connection is not a fixed thing handed down to you by the universe. It's a system. And like most systems, it has variables you can actually influence. The hardware in your home, the router, the placement, the physical environment, all of it shapes what you actually experience day to day. And some of those variables are changeable with things you already own. The copper wire technique is not a miracle. I won't pretend it rewrites the rules of physics or transforms a basic internet plan into a fiber optic experience. What it does is work with the physics that's already there, the same physics that powers every antenna on the planet, and gives your router a small but meaningful assist in doing its job. What I find interesting about techniques like this is not just the practical benefit. It's what they represent. The idea that with a bit of understanding, knowing why things work the way they do, you can make real improvements to your daily life without spending money or waiting for someone else to fix it for you. That's a kind of freedom that doesn't get talked about enough. Try it. Spend 10 minutes. Test it before and after with a Signal app. See what happens in your specific setup, and then make your own assessment based on real results rather than what you've been told to buy next. If this gave you something useful, a new way of thinking about your setup, or a practical trick that actually moved the needle for you, consider subscribing. I keep looking into the overlooked side of everyday technology. The techniques that don't make it into marketing materials, but absolutely make it into practice for people who know where to look. New content drops regularly, and the bell will make sure you don't miss it. Go grab that wire.